Hello everyone. So for this first video, I'm going to show you a way to compute the integral from 2 to infinity of pi of x, pi cube minus x dx, where pi of x is the number of primes less or equal to x. We'll see that the result is quite surprising. It involves not only the function pi of x, but the number pi. How can we do that? So the thing to see is that there is no way to compute pi of x. We know the asymptotic behavior of the function, but we do not know, we don't have an expression for it. So what's the idea? Well, the first thing to say is that I'm going to consider the list of prime. So I will write them P1, P2, P3, and so on and so on. Increasing list of prime number, so P1 is equal to 2, P2 is equal to 3, and so on and so on. Okay? And the thing that we can say first is that I is equal to the sum for k greater than 1 of the integral between pk and pk plus 1 of pi of x, x cubed minus x dx. And why is it interesting? Because how many prime number is there between pk and pk plus 1? Well, by the very definition, pk is the kth prime number. So between pk and pk plus 1, there is exactly k prime number. So I get the sum for k greater than 1, k, the integral from pk to pk plus 1 of dx divided by x cubed minus x. Okay, that's much better. And now I only have to compute this last integral, depending on pk, of course. So my first fact number 1, is that, okay, by standard algebraic computation, but you're going to believe me, that x cubed minus x is simply equal to 1/2 of minus 2 over x plus 1 over x minus 1 plus 1 over x plus 1. Okay? And now it's extremely easy to find a primitive of this function here. Okay, so what can I do now? So I know that I will be equal to the sum for k greater than 1 of k, and the primitive of the function that I had was simply minus log x squared plus log of x minus 1 plus log of x plus 1 between pk and pk plus 1. Right? And there was a 1/2 before all that. I will just write it here. So I have 1/2 the sum for k greater than 1 of k, and I will just write that all together, and I will have log of x squared minus 1 over x between pk and pk plus 1. So this gives me 1/2 or the sum for k greater than 1 of k, and I will just write it like this: log of 1 minus, sorry, there is a square here, 1 minus 1 over 1 square between pk and pk plus 1. Okay, now I have to compute this function, log of 1 minus 1 square between pk and pk plus 1. Okay, but to simplify the notation, I will just say that this is equal to 1/2 the sum for k greater than 1 of k, and I will just write it like this. I will write uk plus 1 minus uk, where uk is simply log of 1 over 1 minus pk square. And actually, this is, well, almost done. Why? Because if I can't really compute this directly, but you can notice that it's almost a telescopic sum, almost. And the right tool to compute this kind of sum is what we call the Abel transform. It's an integration by parts, but a discrete one just for sum, not for integrals. So how do I deal with that? I would write it as the limit when n goes to infinity of what? Okay, so first I will have the sum for k equal 1 to n of k uk plus 1. And since I want a telescopic sum, I will write it as minus k minus 1 uk. Okay, this is exactly a telescopic sum. The problem is that I have a minus k minus 1 uk and I want a minus k uk. So I have minus the sum for k equal 1 to n of uk. All right, this is equal to 1/2 the limit when n goes to infinity of what? Okay, the telescopic sum gives me the following. So for k equal 1, I have just 0 times u0, so it's just, well, it's 0, okay? And so I'm just left with n, un plus 1, minus the sum for k equal 1 to n of uk. And there is something I'm not going to already explain, but from the very definition of uk, I have that un plus 1 is equivalent to minus 1 over Pn plus 1 square. And we know the behavior of Pn actually. Well, we know that Pn is something like n divided by log of n, okay? And because of that, I will see that this term, which is here, it will actually goes to 0 when n goes to infinity. So what do I have left? I only have minus 1/2 of the sum for k from k equal 1 to infinity of uk. Okay, that's perfect. And now I can finally find the sum that I wanted. So I have I is equal to minus 1/2. I recall that uk is a log. So actually, what do I have? I have the sum of log is just the log of the product. So I have the log of u1, u2, u3, and so on. And this is simply equal to minus 1/2 log of 1 minus 1 over 2 square, 1 minus 1 over 3 square, and so on. And there is a fact that I'm not going to explain here, but it's kind of standard. So this is my fact number 2. We have that the product for n greater than 1 of 1 minus 1 over Pn square minus 1, so we take the inverse of that, it is simply equal to the sum for n greater than 1 on 1 over n square. And this is a well-known sum. It's equal to pi square over 6. So because of that, I will be equal to minus 1/2. What I have between my parentheses is the inverse of the result that I just had before. So it's going to be ln of 6 over pi square. So it's going to be 1/2 of log of pi square over 6. And the final result is going to be log of pi divided by square root of 6. So we get this beautiful result. I is equal to log of pi divided by square root of 6. Thank you for listening.